For this example, we're going to study a simple batch processing technique that is very useful and where we want to make sure that we can process data as fast as we can, but without the risk of going over the memory limits. Without this kind of control, besides the memory, there are other potential problems that can occur during the process. One of those examples, or some of those examples, are network saturation, excessive use of sockets, or even an excessive context switching inside the application. The solution is going to be actually somehow simple. All we need to do is to create a number of parallel workers that are going to perform the same operation. So we're going to need like a number of goroutines to do that job. For that, we need to, so the challenges for that, or the steps that we have to take care of, is we need to have a way to keep these goroutines alive while the data is available. And then we also need to figure out how do we even send the data to those coroutines in the first place. The answer is going to be pretty simple. We will use channel and sync groups. For now, you can think of channels just as a simple priority queue that will be receiving the jobs, and then the goroutines will be pulling them out one by one. As for the sync group, think of it just as a container that will keep track of the in progress and completed jobs. Again, this is just a very simplistic explanation. In short, the solution is going to be just creating a pipeline where the reader obtains items one by one, it pushes it to the channel, and then each one of the workers will pop an item, process whatever that means, like storing in a database, and then repeat the process until there are no more items available. Let's start with something simple, with something that it will be more like the kind of starting point for any batch processing that you will write. So let's start with a process that simply reads something like this. Will come from a file probably, or a Kafka topic or something that it will be pushing data to your program that you can do very, very fast. Again, let's pretend that it's a data source is a file that has 500 records, and then you have to push these records to the database. And this save user function that I have over here is just a simulation where I have like some random delay that it can take anything from 1 millisecond to 100 milliseconds, and it's going to print a dot every time that we finish one of these insert operations. And we're going to be counting how many of these items we actually process. So if I run this, of course this is really slow. This is not what we want, and this is again the starting point that we want to optimize, right? Or otherwise this will take forever. Let's leave it running to see how long will it take, and I'll start writing the code for the changes that we want to make. As I said on the presentation, the first step is to define the number of workers that we want to use. You can see it took 25 seconds to process sequentially the 500 items. So if I write a real program that uses 5 workers to start with, this should go down to something like 5 seconds, right? So the first step, if you remember from the slides, will be to create a channel that is going to be the source for the jobs. It's going to be the connection for the entire pipeline that we're trying to build. So let's create like that jobs channel, and we use the make statement for that. And the channel is going to be receiving items of the type user. We want a channel with at least 1 item capacity because we just want it to be serving as buffer between the process that reads the data and then the process that is going to be populating the database. So now my step number 2 is going to be to create the workers. So here I'm going to say for let's equal 0, number of workers defined by my arguments, and then we do I++. So here if I have to change this definition. So the first thing that I need to know is like this loop that is reading the data, instead of calling the database directly, is just gonna be putting the user record in the pipeline, so it has to be sent to the channel. So the syntax to do so is we define the channel and we pass the user here. This is failing because we don't have user defined here, but basically what we're saying here, every time I read a record from the database, from the text file, we're going to put that record into the channels, into the jobs channel. So let me comment this for a second. If I run this program, because remember this is a queue, what it's going to happen is my loop is going to put the first user into the channel, but because it has capacity 1, that means that for the second time that the loop runs, which is going to be when I equals 2, then it's going to try to put the second user into the channel, but the channel is blocked because it doesn't have capacity to keep receiving tasks. So my program is going to be blocked. Nothing can happen after that point, and the loops gets stuck, and my entire program gets stuck. Let me comment this because we're not using it. So if I run it right now, I should receive an error from the Go compiler saying that not from the Go runtime, saying that the program got stuck that we have a deadlock, which we can see here. I just ran the program and that's what I was expecting, right? So now in order to resolve that, what I need to do is to actually create the workers now. So now let's do that for real. So here we're creating the workers, but also if you remember the workers, they have to run in a separate Go routine, or what you might know as something similar to what you know in other programming languages as a thread. So we know that we start a new Go routine with the Go keyword, and we're going to create a lambda function here. Let me comment this because I have to do something here. So now, okay, so now I have 10 workers with this lambda, and here I don't have a user, so I have to make the worker to the queue each one of these users from the channel. So to do so, I will do user equals to jobs channel. This is gonna the queue one of the items. It's gonna put it, it's gonna assign the value to this user variable, and then I can make use on each one of these items. There's a reason why I'm commenting this. I'm gonna get to this point, but for now, know that now we have 10 workers are gonna be queuing an item, and they're gonna be processing, or they're gonna be sending it to the database. This is still incorrect. Like if I run this code, you're gonna see that we have 5 workers, so we should see 5 dots printed, that meaning that we processed the record correctly. But then because I'm just queuing one item from the channel, that means that my solution is incomplete. Let's run it. We should see again 5 dots, and we should see a deadlock again. You can see here the 5 dots, and you can see the deadlock. And the reason again is simple, right? Like we are trying to push data over and over to the channel. However, my workers, which I have 5 of them, are only queuing one and only one item. So what I need to do is what I was describing on the slides. We need a way to keep the workers pulling data over and over from the channel as well. So to do so, we're going to change the way we queue items from the channel. Instead of following this syntax, here we're going to see equals range channel, and this is going to be more than enough to tell each one of these workers to keep reading data from that channel for as long as the channel keeps pushing data. Okay, so let's run this. Here there is a problem though. If I run this code again, when we reach the 495 items, which means that there are only 5 items left, this loop is going to be pushing those 5 items to the workers. But then as soon as the worker takes a new user here, then that means that that user is no longer in the channel, and this loop can continue even before I save the object in the database, which means that actually my program can continue the execution before completing the last 5, because I have 5 workers, operations. So in this particular case, we should only see 490 something items processed. Like there is no real guarantee that how many are going to be completed, because it depends a lot on the speed of the database, but it will be at most 495, 496, no more than that. So here, because I have this commented, it's not going to be visible, but at least on this example, we can see already the benefits. At least we see that we went down from 25 seconds to sort of like 5 seconds, which means that our workers are already doing the processing. But then here I'm going to introduce another error. This is a very common error in any programming language, to forget about this concurrent access to a shared resource. So the process items counter, it's a shared variable for the entire program, and then we have multiple workers incrementing it at the same time. So this operation is not safe. If I run my program, it's not going to throw any error, but it's not going to give me the expected behavior. So let's see it in action. Like if I run it, you can see that it gives me 494. If I run it a second time, it might give me a completely different number, because of that concurrent access might be the same. But you get the point, like this is a shared resource. How do I know that this is gonna fail? If I go here to the terminal and I run my same program with the raise flag, you can see here that the Go tooling is already telling me that there is a data raise, and it even tells me where it is, which is in this shared access variable. So the right way to do an operation that is thread safe for these kind of scenarios, we are gonna need to redefine this as an int64. Now here is the operation that we need to make safe. So to make this kind of operation safe, the Go programming language has something that is called the atomic access. So here we can take basically an int64. We're going to pass the reference to the memory to that item, and we're going to increase it by 1. It's kind of like it's exactly the same as the plus plus that we had before, but this is thread safe. Now if I run my program again here, you can see that I'm still running with the raise flag, but now Go is not detecting any data raise here. So cool, we resolved that problem, and we see that, as I expected, we're not processing the 500 items because of what I say. Like once the value is the queue here, this loop continues and the program finishes. So we need to have a way to tell the program to actually wait for the completion of the database operations for each one of these users. And that's where we're going to have the sync group that I mentioned before. Sync, wait group. And this is kind of like a safe counter as well. So now every time that we're going to be pushing data to the channel, we increase that counter by 1. And then every time that we actually complete that database operation, like the entire cycle here, this is gonna decrease the counter. So this increases every time that there is a job put into the sync group, and this decreases that counter. Keep in mind that if I put it here after the database completion, then that means that this code might not be executed because of the same reason. Here we're telling it that we're terminated, so the program can finish at that point. So we need to make sure that it's put in the right place. Now here we have the counter increase and the counter decrease, but we need to set a point in the program where it actually has to block the execution of the program until that counter reaches 0. And we're gonna do that before printing. So if I do sync the wait group wait here, that means that it's going to have that it's going to block the entire execution of the program here until the internal counter here reaches 0. So this is going to work. Let's make it fail once. If I don't do the done here, or if I increase by more than 1 here, then this counter is never going to reach 0 and my program is going to get locked. So let's do that. Here is going to complete the 500 dots, and yeah, you can see that here that's what we were saying, like everything falls asleep because I did a wrong usage of here. Like I increased by more items. At some point this gets blocked forever, and that's what it's telling me here. That's the deadlock. So let's correct it, and this should be the first time that we're able to run this program flawlessly. Yeah, you can see now completed the 500 items in about 5 seconds. And if I want to run the same program with more workers, remember that's the W flag that we're passing, this should reduce the execution time even further. 2 seconds if we do 30 workers, 800 milliseconds, and so on. Keep in mind that for this particular number, the number of workers, there is no magic formula to do so. So you're going to have to be pretty much figuring out what are the resources that you have for the program. If you set way too many workers, then that's going to create maybe back pressure in the memory of the program, because like essentially everything is alive at the same time as well. And you might, if you make it like super crazy, say let's do 1,000 workers, and actually let's do, remember that I was creating 500 jobs, let's do 1 million jobs. Oops. This might fail at some point as well. Let's do 100 million jobs, and then let's do 1 million workers. Here you can see that I'm also reaching the limits of my program if I go too crazy. That's why I was saying, like, just keep in mind that this is not the silver bullet. You have to know the limits of your system. So let's do 10,000 items, and let's do 100 workers. You can see that it's going super fast, but then again, make sure that whatever you're using, like if it was a database that you're hitting downstream, make sure that it has the capacity to handle the number of parallel works that you're trying to use. And that's pretty much it. I hope you find this information useful, and I'll see you in the next one.